thanks a lot to the organizers for giving me the opportunity to speak in front of such a big audience. So I will report here on a variety of joint work with Simone Cecchini on trying to use the Dirac operator to prove kind of quantitative distance estimates in the presence of lower scalar curvature bounds. And maybe to start, I will, and we have already seen this in the previous talk, but let's give you a quick reminder on the Dirac method and scalar curvature. So the basic version is that if you have a Riemannian spin manifold, I will not give you a definition of that, but what's important is that it gives you the spin or Dirac operator, which acts on the spin or bundle, and it has a explicit description in terms of some algebraic gadgets and a connection. And sort of the algebraic gadget is the Clifford action, which is basically an endomorphism on the spin or bundle for every covector on your manifold. And the connection to the scalar curvature is given by the famous Schrödinger-Licherovich formula, which tells you that the square of the Dirac operator is a connection Laplacian or the rough Laplacian plus the scalar curvature. And this kind of formula can be used in a variety of ways to connect properties of the Dirac operator to geometric properties involving the scalar curvature. And the most basic version is the following. If you integrate this formula, say, and suppose we are in a closed manifold or you work with compactly supported sections, then you obtain something like this. And you obtain this. And if you now suppose you're given a spinor which is harmonic, and also suppose that on the manifold where you're working on, the scalar curvature is non-negative, then you can, as we've seen, combine this to conclude, well, this now is 0, this is non-negative, so then this must be 0 as well. And you conclude that the section you started with is parallel. And this in particular means that the scalar curvature actually must be constant, equal to 0, because if it was positive somewhere, then if the section is non-trivial, because it's parallel, it must be non-trivial everywhere. And then you can see from this formula that the scalar curvature cannot be positive at some point, if you assume that the section was non-trivial. But actually, there's something more is true. So if you have a non-trivial parallel spinor, then we actually know, because of the precise shape of the curvature tensor on the spinor bundle, that the rigid curvature must vanish. So that there is actually some kind of stronger rigidity statement already built in just from this spinor method. And sort of that's the sort of basic logic of this method. You assume something about the scalar curvature, you take a non-trivial harmonic spinor, and then you can conclude geometric consequences. And for this to work in practice, you need some source to generate non-trivial sections of the spinor bundle. So you need some sort of black box, say, which does something and produces you a non-trivial element in the kernel of your operator. And if you have such a machine that does this for you, then by sort of arguments of this kind, you get geometric consequences for the scalar curvature. Okay, And what can you use here? Well, the sort of most common thing that would be a Thier-Singer index theory. That is sort of has a topological flavor, and you can sort of deduce existence of non-trivial solutions from characteristic invariants, like the head genus. But it actually doesn't have to be. So that it's not. This is maybe the most common thing that is used. So that Thier-Singer index theory and all sorts of possible generalizations of that. But there is also, for instance, in the case of the positive mass theorem. There are sort of Lax-Milgram type arguments that in specific situations can be used to produce non-trivial harmonic sections. This is sort of used in Witten's approach using spinors to the positive mass theorem. And I decided that for this talk, I will not so much focus on this aspect, how you produce harmonic sections. I will instead tell you more about how you use arguments of this kind to produce geometric consequences. And this is also the kind of new thing that we added in our papers here. And that's why I focus on that. All right. But I will sort of along the way give you like sample theorems of sort of concrete statements that you get using these techniques. And as we already seen, the sort of most basic result, or the first result of this kind, is sort of due to Lichterowicz, which says that a closed spin manifold of non-vanishing A hat genus does not admit positive scalar curvature. Okay, so that's sort of this argument. You can use it to exclude positive scalar curvature. In the end, I will try to come to a little bit more quantitative things. And for that, this kind of formula needs to be refined a little bit. And let me actually already come to this at this point. So there's a slight refinement of the geometric argument already in this basic stage. Slight refinement of the geometric argument. And that is that you can refine this integrated formula a little bit and improve it essentially by a factor of n times n minus 1, where n is the dimension. So this can, there again, you get the scalar curvature. And instead of the connection, you get the so-called Penrose operator applied to your spinor squared. And this is something that has the same type as the connection. And explicitly, the formula is this. So it is the connection plus 1 over n times the Clifford action times the Dirac operator applied to you. And that is sort of for this kind of arguments where you just want to exclude positive scalar curvature, that's not important. But it kind of slightly refines the sort of spectral estimates that you get out of scalar curvature. If you assume sort of an explicit positive lower bound, you get some consequence on the spectrum of the Dirac operator, and that refines this bound by this factor. And sort of this observation, or the fact that you can refine it like this is originally due to Thomas Friedrich, and you can use this to show that any eigenvalue of the Dirac operator has a lower bound, which I mean is the infimum of the scalar curvature over 4, which comes from here. And from this slight refinement, you get this additional factor of n over n minus 1. And there's also a rigidity argument. If you are in the equality case, you can analyze this Penrose operator a little bit more and conclude that the manifold must actually be an Einstein manifold in this case. We will see something very similar that will happen later in what I will explain you afterwards. But for now, let's move on a little bit beyond the sort of very basic version of the Dirac method, where you just use the Spinor-Dirac operator as it is, and let's try to augment it a little bit so that you can prove more with it. And what I will come very soon, we have already discussed before, namely the problem with Lichner-Rovitch result, in a sense, is that this a hat assumption is, in a sense, very restrictive. So, for instance, you cannot deal with the torus in this way. And to deal with the torus in this way, you need to augment your method. And the first augmentation that I will discuss, which is also classical, is by twisting your Dirac operator with a vector bundle. So there what you do is, in addition to the structure we had before, so you start with a Riemannian spin manifold, then you take an additional Hermitian vector bundle, and you just tensorize that bundle on your spinor bundle. And you also choose a metric connection on your bundle. And then you can, in the same way as before, produce a new kind of Dirac operator on this twisted spinor bundle. And it also satisfies a Schrödinger-Lichner-Rovitch formula. And the only difference is that now this vector bundle E and this connection that enters in the form of an additional curvature term, which encodes the curvature tensor of E, or it encodes a contraction of the curvature tensor of E and the Clifford action on your spinor bundle. And an important example of this is if we have a map from your manifold, let's say, to the sphere, then you can pull back the spinor bundle of the sphere. And if you, let's say, assume in addition that your map is area non-increasing, or you can also just for simplicity assume that it's distance non-increasing on one Lipschitz, then you can give a lower bound of this curvature term by minus n times n minus 1, which is incidentally, or not so incidentally, the scalar curvature of the sphere. And then if you have that, you can use this formula and now use this additional term and try to sort of quantitatively balance the scalar curvature term with this twisting bundle term, and deduce consequences in many different kinds of consequences. And this idea has been used in many different ways. So the easiest thing would be if this bundle E here was flat. Then this term would drop out, but this is usually not so useful, at least if we work with finite dimensional bundles. If we go to infinite dimensional bundles, then this is useful, but in the first cases of this method, you cannot, you couldn't use flat bundles here, but you could use sort of almost flat bundles. So for instance, if this map here was not area non-increasing, but let's say epsilon area contracting, then you could get here a bound. You could basically get the same bound here with an epsilon, and then you could try to make this as small as you want if you are in a situation where you can choose epsilon small enough. And sort of the concrete result that was proved using this idea is that area enlargeable or enlargeable spin manifolds do not admit metrics of positive scalar curvature, which is originally due to Gromov and Lawson. And sort of, for instance, the torus can be treated in this way. Okay, that's sort of the first kind of augmentation that I wanted to discuss. So you can add a twisting bundle. At this point, I also want to discuss a little bit, it's a bit of a digression, but in addition to this A hat genus, there are sort of other kinds of index obstructions. For instance, the alpha genus of Hitchin, which is, for instance, important if we want to deal with these examples of exotic spheres that have a non-trivial, that don't have a positive scalar curvature, which we discussed in the discussion after the previous talk. And in fact, for simply connected manifolds, this alpha genus is a complete obstruction to positive scalar curvature due to Stefan Stolz. And this is sort of only true in high dimensions, starting from dimension 5. And there is sort of one more generalization of this, which is the so-called Rosenberg index, which now kind of tries to emulate this Hitchin stuff for the non-simply connected case. And formally, you can actually understand this, this thing in terms of a Dirac operator that comes from a twisted bundle, from a twisted Dirac operator, where you use an infinite dimensional vector bundle as your twisting bundle. And in a sense, one could say that this is perhaps the most general index obstruction that is known on closed spin manifolds. Unfortunately, it's not a complete obstruction to positive scalar curvature, like in the simply connected case. Because there you have sort of other obstructions which do not come from the Dirac method, like minimal hypersurfaces. All right, but let me go on. So next, I want to focus a little bit more on this case. So here we have seen that if we make this curvature, let's say arbitrarily small, you can get some obstruction results. But you can actually, using this idea, you can make this very precise and get a very precise, sharp result, which is due to Yarul. And that says, if you have a closed spin manifold and the scalar curvature is bounded below by the scalar curvature of the sphere, and you're giving a area non-increasing map to the sphere, yeah? And then you kind of want to compare the scalar curvature of M to the scalar curvature of Sn, like here. And if you have such a map and it has a non-zero mapping degree, then the theorem tells you that it already must be an isometry. So in a sense, this situation is very rigid. And the way this is proved, this is precisely as on the previous slide, that you use this twisting bundle that you get from pulling back the spinor bundle of the sphere along this map and analyze this situation very closely. And sort of
bigger than 2.
Yes, yes, and bigger than 2. Yes. Right. And sort of in this case, what happens is that in this formula, this term and this term precisely balance out, and you get some rigid conclusion if they match up. All right, and sort of this idea, this original idea of Yarul, this has been generalized in the following way. So first by Goethe and Semmelmann to more general kinds of target manifolds than the sphere, and then very recently by John Lott also to manifolds with boundary if you bring the mean curvature into play. And I will state this result of Goethe Semmelmann and Lott together. So actually the result of Lott includes the original one. And it says something very similar like this. So now you start with 2 manifolds, and you start with a smooth map of spin map of non-zero A hat degree. I'll not explain in detail what this means. As a sort of already important special case, you can assume that let's say both are spin and they have the same dimension. And they have, and F is a non-zero degree. But there are sort of also more general situations where they don't have to have the same dimension. And then there are a bunch of conditions, which some of which are more important maybe than others, but for the current statement of the theorem, they're all, of the current proof method, they're all necessary. So the first condition is that F is area non-increasing. Second condition is that on the boundary, it's actually one Lipschitz, so it's distance non-increasing. And then there is a sort of non-trivial sort of positivity condition on the curvature on the target, namely that the curvature operator is non-negative and the boundary is convex. And that means that all the eigenvalues of the second fundamental form are non-negative. And also there's sort of a topological condition, namely that the Euler characteristic of the target is non-zero. And then you assume, like above, that you have a scalar curvature comparison situation where you bound the scalar curvature of M below by the pullback of the scalar curvature of the target along the map. And the same should hold for the mean curvature. So this is the mean curvature of the boundary inside of M. And if that happens, then actually you have an sort of, this is sort of an extremality statement that you actually cannot increase it any further. So in this case, you actually have equality. It's a typo here, it should be equality here. And for both the scalar and the mean curvature. And you also have a rigidity statement that under some additional positivity assumption, you get that F must be a Riemannian submersion. Or in this basic case, again, that F must be a local isometry. All right, so this is kind of I think, I mean, this is relatively recent, but if you sort of exclude the case of boundary, this is kind of the thing that was known until a few years ago, what kind of thing you can do with the Dirac operator and trying to prove sharp estimates, or trying to prove sharp estimates. And now let me come to sort of the problem that I actually want to address using new methods. That's a conjecture due to Misha Gromov, which says the following. So now the idea is you start with a manifold which does not admit the metric of positive scalar curvature, but you look at the cylinder over this manifold and you try to put a metric with a positive lower scalar curvature bound on that. And a priori, there is no restrictions to that. If you have a compact manifold with a non-empty boundary, you can for instance, by H principal arguments, you can find metrics with any sort of lower scalar curvature bounds, or even lower sectional curvature bounds if you want. But this doesn't mean that if you have that, this couldn't have some kind of other geometric consequences. And sort of this conjecture predicts that there is some kind of distance estimate in such a situation, namely that the distance between the two boundary components you get must be bounded. And it must be bounded, if you sort of normalize the scalar curvature to something specific, it must be bounded by a specific constant. And the specific constant here is 2 pi over n. And I'll say on the next slide where this constant comes from. But before that, let me sort of mention a little bit what kind of approaches have been used to attack this conjecture. And so the first thing in the metric inequalities of scalar curvature paper by Misha, this was proved for the torus and related manifolds using a symmetrization version of the classical minimal hypersurface technique. And this kind of approach sort of only applies to the torus, and not only the torus, but sort of anything where you have this kind of homotopy theoretic obstructions that are related to the minimal hypersurface method. And for instance, so you cannot deal with sort of simply connected spin manifolds where you only have these A-hat obstructions in this way. And myself and Simone Cecchini, we used a sort of modification of the Dirac operator to prove this in the presence of a suitable index obstruction on M. And there's also sort of a more general version of the minimal hypersurface method that I'm sure will be discussed in some of the later talks in the seminar, which is called mu bubbles, which is in a sense parallel to this augmentation of the spinor Dirac operator that I'll discuss today in this talk. But sort of that will be sort of the main focus of the rest of my talk today. But before I come to that, how we use this the spinor Dirac operator here, let me answer where this constant comes from. So there is an explicit example for this for such a metric on such a cylinder, which allows you to almost realize this bound to pi over n. And that is a sort of a specific kind of warped product metric, which looks like this. So in general, if you start with a warped product over an interval, let's say like this, and sort of you put a warping function in front of some arbitrary metric on your manifold M, then you can compute the scalar curvature of the resulting metric in terms of the scalar curvature of this cross section and some additional terms here. And these additional terms here, they, if you sort of write them in terms of this function here, they depend on some sort of differential expression in terms of the logarithmic derivative of this warping function phi. But this has a geometric meaning. So in fact, this logarithmic derivative here is the mean curvature of this cross section, let's say at the point x. So in a sense, what you can say is that you can express the scalar curvature on this warp product in terms of the scalar curvature on the cross section and the mean curvature that you prescribe using this warping function. And if you now want to, let's say, make this as in this conjecture, let's try to make it equal to n times n minus 1. Then what you can do is, well, let's say we choose this to be scalar flat. Let's make that go away. And then you can sort of solve this expression and you get an explicit solution that looks like this. And the sort of mean curvature that corresponds to this, that is given by this tangent function here. And that tangent function here has the property that at the boundary points of this interval, it blows up. So it goes to plus or minus infinity, depending on which side you are. All right. So that kind of concrete example motivates this constant 2 pi over n. And here's maybe also a plot of how this function phi looks like. So in the case n equals to 2, this is just a cosine and gives you the warped product description of the 2-sphere. And in higher dimensions, it's something different. So you get some kind of, because of this yeah, because of this very high root you get here in high dimensions, you have sort of a kind of strange kind of singularity. It's a singularity here that you might not be used to. But this is also something which is kind of, you know, follows from this fact that the scalar curvature grows like this in high dimensions. That sort of this kind of canonical model space you have for this kind of problem also behaves in such a way. Okay, and now the question is, what I want to come to is, how can you use the Dirac method to treat this conjecture, or more generally to, you know, try to treat some sort of extremality statements for Watt products of this kind. And what you do here is the following. So you essentially use the Dirac operator, but you augment it a little bit. And the first augmentation is that we need some additional algebraic ingredient. And the most basic thing you can do here is you sort of double the spinor bundle and you put the Dirac operator sort of in odd in this way that it becomes odd again. And then what we do is we use this double Dirac operator and add a potential term. And this potential term also uses some additional algebraic gadget, which in this basic case that I want to discuss is just given by this Pauli matrix here. In general, this can be understood a little bit more conceptually in terms of Clifford algebras, for instance. But for the sort of basic argument that I want to present, this is enough. And then you take any suitable smooth function and you add it to your Dirac operator. And then you try to do the same thing as before. You want to derive some kind of Schrödinger-Lichner-Robic formula. And you can just compute, in this case, you can just compute the square of the Dirac operator, square of this new modified operator. And you get the square of the Dirac. You get the square of this term, which is this. And then you get some mixed terms. And this was chosen in such a way that this and this anticommutes. And for this reason, you get here the Clifford action of the differential of this function psi times this Pauli matrix sigma. And then you can, let's say, use the Schrödinger-Lichner-Robic formula again. You can rewrite this like this. And if you now try to also plug in this Friedrich type argument, you can bound this below by n over n minus 1 times the scalar curvature plus this term here. So this term here you just got from here, and this we got from this using. I mean, this is a little bit more involved if you how you write it, but essentially that's what you get. That from this you get this lower bound, and from this here you get sort of this lower bound by just estimating this by the norm of the differential. And then the game you want to play is that you want to choose your function psi appropriately such that it's precisely, or let's say, overshoots the scalar curvature lower bound you plug in here. So it's a little, it's different than what happened in the case of a twisting bundle, but in the end, the argument is very similar. So you have some additional freedom and you want to choose it in such a way that it kind of precisely counterweighs the scalar curvature lower bound. And for instance, if you want to approach this bandwidth conjecture that I mentioned, you can choose a function which essentially is given by the mean curvature that comes from this swap product that we had before. And so here you write psi as a function of x, where x is, let's say, a suitable distance function where you are on your cylinder or your band, let's say, and then you take x to be sort of a one Lipschitz function to the interval minus pi over n, say. Let's say, assuming that the distance between the boundary components is bigger than 2 pi over n, if you as a by sort of as a contrapositive argument, assume that, then you can find such a function, and then you can plug in the tangent. And what you get then is, for this expression that's relevant here, this tangent satisfies precisely this differential equation that this is minus n squared over 4. And if you have assumed that the scalar curvature is bounded below by n times n minus 1, you precisely get a n squared over 4, which balances out. And then you can see that you can use arguments of this type to sort of exclude the possibility that this is strictly bigger. And if it's equal, you might get some rigidity. But this part is a little bit more subtle because in the rigid case, it actually collapses. So you have to deal with this a little bit differently. But that's the idea. So it's kind of a different augmentation of the Dirac method using a suitable potential, and then you play around with it to balance the scalar curvature bound. Okay, and maybe as a sort of additional remark, this is actually also, in a sense, a kind of twisted Dirac operator, because you can actually define a different kind of connection like this, and then this Callier's operator here is really the Dirac operator corresponding to this modified connection here. Okay, and sort of using these techniques, what I proved is that whenever you have a spin manifold with a non-vanishing Rosenberg index, so this kind of very general index invariant, then this bandwidth conjecture holds. And in particular, it holds, if you sort of combine this with the result of Stefan Stolz, it holds for all the simply connected manifolds of dimension at least 5. All right. So
in your remark, there is no psi on the right-hand side.
Oh yeah, that is right. The psi should be here. Yeah, thanks. There's a typo. All right. So that's the first kind of result, and we have seen that sort of the mean curvature plays an important role in many of these kind of arguments, but so far for like this kind of result, it kind of played an implicit role because it's built into this potential here, but it wasn't made explicit. And so in a sort of additional next joint paper with Simone, we made this more explicit by studying the same kinds of problems, but on a manifold with boundary. And for that, let's say now first state our result. So I'll give you a slightly more general version of this conjecture now in this result. Let's say we work with a so-called band, which is a compact manifold just together with a decomposition of the boundary into two parts, which are non-empty unions of components. So this could be something like this. And this is actually sort of the most natural kind of thing where you would try to state this kind of conjecture. And our statement is that now we can bring the mean curvature into play in the following way. So we start with such a band, and now we assume some sort of index obstruction on the boundary. namely that it's a heterogeneous, is non-vanishing, and the scalar curvature is bounded by n times n minus 1. And then we have sort of a refinement of this distance estimate in the following way. If we have an additional bound on the mean curvature, which is given by the tangent function here in terms of some argument between 0 and pi over n, then the consequence is that the distance between the two boundary components is at most 2 times this argument here. And this kind of corresponds precisely to this model situation, this warp product, where you just go to the distance from minus L to L. And in this way, we also got a rigidity conclusion that if we have equality here in this estimate, in addition to the assumption, then we actually get that the manifold V is already isometric to a warp product of this form, where this is precisely the this warping function that I mentioned in the examples a few slides ago, which is precisely the motivating example for this conjecture. And also, moreover, in this case, the cross section that you get here admits a parallel spinor. So in particular, it must be Ricci flat. I mean, that you can actually already deduce in other ways, but this is sort of already witnessed by the spinor approach here in the terms of a parallel spinor. And sort of in particular, you can sort of also, if you have that statement, you can also again get this estimate as a corollary, because if you look at this function here, this goes to minus infinity as L goes to pi over n. So if you start with any compact manifold with boundary, then if you really assume the boundary is there and it is non-singular, doesn't collapse, then the mean curvature will be bounded by some potentially negative constant, and you can undershoot it by just choosing L sufficiently close to pi over n, and then you will get some lower bound, some upper bound here, which is smaller than 2 pi over n here. Okay, so this is one of the results that I wanted to mention. And in fact, this is part of a sort of a more general kind of comparison argument for warped products using the Dirac operator. And let me maybe mention another application of the same kind of comparison result. And then in the end, I will state the comparison result in like the technical comparison result in full generality. So you can apply the same kind of ideas of using a Dirac operator of potential to prove something about annuli in space forms, for instance. So here we start with either the sphere, Euclidean space, or a hyperbolic space in general, any space form of any curvature you want. And you fix some base point. And then you just take an annulus of some, where you fix some radii, t minus and t plus. And in the case of the sphere, you also assume that you don't go all the way to the opposite point. This is sort of this assumption here in the case of the sphere. And the theorem that we have is that at least in odd dimensions, if we have a Riemannian metric on this annulus, so another one in addition to the standard one, which on vectors has this bound. So for the length of any tangent vector with respect to G is bounded below by the corresponding length with respect to the standard space form metric. And you have the lower bound of the scalar curvature, where you compare it to the scalar curvature of the standard metric. And you also have at the boundary of your annulus, you have a bound on the mean curvatures correspondingly. Then you already get that this metrics are equal. Yeah, so these are kind of this kind of annuli are extremal in this sense that you cannot simultaneously increase the metric, the scalar curvature, and the boundary mean curvature. And notice that here you allow cases where either the scalar curvature, or let's say the curvature itself here is negative, or the mean curvature is negative. So in the case of the sphere, here the mean curvature will be typically negative. And in the case of, let's say, hyperbolic space, this here will be negative. So this result is kind of a different type than this comparison result of Goethe-Semmelmann and Lott that I mentioned at the beginning, because you can allow sort of negative curvature on your target here. And this is because this is not a, sort of a comparison result of the manifold as a whole, in a sense. It's kind of a parameterized comparison results for warped product, where you sort of compare slice by slice of heuristically. And that is sort of the reason why sort of you can allow some negativity here, which you cannot in this other kind of result. All right, so these are sort of the main results that I wanted to mention. And maybe sort of for the rest of the talk, I guess I have about 15 minutes. Is that right? Then I will try to explain you a little bit in more detail how the tools, sort of the geometric argument that goes into this theorem and this theorem, sort of they are essentially follow from the same kind of arguments. And I hope that maybe this kind of computations might be useful for someone else, or maybe it could be transferred to some other situations beyond the Dirac method. Let's see. So as I said, this is essentially something about warped products over intervals. And let's set up a general situation where you start. Let's start with a band, and we are of course allowed to combine these both augmentations, so both the potential augmentation and the twisting bundle augmentation of the Dirac method together and prove something with that, and that's what we're going to do. So we choose an additional Hermitian vector bundle as well, and let's say we have some compact interval and we have a bunch of functions. I will explain what they mean geometrically. So first of all, we have a function phi, which should go into the positive real numbers, and which is the function that's used to describe a warp product. So this is the warping function. Then we have a function on our band, which goes into the interval, and this is you should assume that you should kind of think of this as the kind of distance function involving the distances to the boundary, maybe at least in these situations that we are interested in. And then you get some additional functions, kappa and nu, which describe some kind of curvatures or some kind of scalar curvatures. Now, before doing that, let's introduce a symbol for the logarithmic derivative of our function phi, which is the mean curvature of the corresponding warp product, and a variant of this mean curvature where you just add a suitable constant that makes computations easier. And we assume that x is 1 Lipschitz, and it maps the boundary points, the boundaries of the band to the boundary of our interval. And then there is sort of a important kind of curvature assumption. So the mean curvature should behave monotonically. And what we assume is that phi is strictly logarithmically concave, which means that the derivative of this function h here is strictly negative, or the derivative of the function f is strictly positive. And then we have an important inequality, which looks like that. And now that might look a little bit strange, or it's maybe not clear where this comes from, but this is in the same spirit as before, that we assume some sort of bound on the curvature. And in fact, the idea that we have behind here is that that this here corresponds to the scalar curvature of some warped product metric. Yeah, sort of this is kind of this sort of corresponds to the scalar curvature of the cross section at a particular point. And that is sort of this mean curvature expression that you've already seen before in this scalar curvature formula for a warp product over an interval. Sort of that's precisely what comes together. And sort of if you have actually a warp product, then you would have an equality here. And what we assume now is that, as usual, we have a bound in one direction. And then we want to conclude from that, if the bound is realized, that we have some sort of rigidity, or we actually cannot we cannot sort of go beyond this bound. And that is sort of our sort of technical theorem that is essentially sort of behind all the things that we've done in this area in a certain sense, or like it's these variants of this are behind of this. And that is the following. So assuming that we are in such an abstract warp product setup, suppose that the scalar curvature now is of geometric G is bounded below by n times n minus 1 times kappa. So sort of the kappa kind of specifies the scalar curvature up to this constant here. And the twisting bundle that you use, that kind of should be used to counteract the scalar curvature of the cross section. So in the case of a band where you sort of your model situation is scalar flat, you could choose this to be the trivial bundle and nu to be 0. But sort of in more general situations, like in this annuli in space form example, for instance, there you would put something here which counteracts the scalar curvature of the cross section, and then you have as you would expect, a bound on the mean curvature on your manifold on the boundary, where you precisely get this mean curvature coming from the warp product as your bound. And then the theorem, sort of the technical theorem that's behind all these results, is if you have a non-trivial section of your Calias operator that we discussed before, which satisfies a suitable boundary condition. And this boundary condition here is given in terms of the interior normal field and this Pauli matrix that we had in our situation. So it's a suitable boundary condition for this problem. Then we can actually conclude that this band we started with is already a particular warp product, namely the warp product that given by the function that we started here. And we can also say something more about this M. So this will actually reduce, so this section will actually restrict to a spinor on each cross section, which is parallel with respect to a suitable connection. And for instance, in the case of the standard, in the case of this bandwidth estimate, this connection you get there is really the standard spinor connection. You get a parallel spinor, and sort of in more general situation, you get something different, but you still get something parallel with respect to a suitable connection. So you can say a little bit more about this cross section depending in which situation you are. And maybe to close off, how do you prove such a theorem? So there, what you have to do is coming back to the beginning of the talk. All you do is you integrate your Schrödinger-Lichner-Robic formula. Now you have boundary terms. You have to use Green's formula and the boundary condition. You get suitable boundary terms, and but in a sense it's the same idea. And if you do this, you get this kind of formula here. And now you can see that everything is set up in such a way that all the terms precisely cancel. If you assume this estimate that we had before. So for instance, let's say if we combine this, and all of this together, then sort of this red part here is bounded below by 0 by assumption. Sort of namely by sort of this assumption here, because this here together will be bounded below by kappa times n minus 1. This will bounded below by nu, and this now sort of this and this together gives you this term n squared over 4, and this gives you this nu times n minus 1, and from above here you sort of get precisely a lower bound with the opposite sign as you expected. So maybe this is a bit fast to follow, but sort of the idea is that we have set it up in such a way that in this formula you get things precisely cancel out, and also sort of this this guy here is non-negative by assumption, and so the only thing that remains is this guy with the Penrose operator. And now basically the idea is if you have a non-trivial element in the kernel, then this left-hand side here is 0, and so you get kind of a situation where you have 0 bounded below by a bunch of things in the middle, bounded below by 0, and that gives you all sorts of consequences by showing because it implies that all the equalities that you have in between, all the inequalities you have in between must actually be equalities, and then you can deduce a lot of things from that. So for instance, I mean, the first thing you conclude, of course, is that the Penrose operator applied to U is 0, and you also conclude that from this term in the middle, that the sort of Clifford action with the differential of your distance function times this sigma acts by -1 on your section. And also because this section must now be parallel with respect to this modified connection, you actually get a formula for the covariant derivative of this. So you kind of see that this satisfies this suitable partial differential equation, which is very strong, which looks like this. And from this, you can, for instance, conclude that with some more computations that the norm of U squared must actually be a constant times your function, your warping function. And you can conclude that let's say you can actually conclude then from this that your differential of your function is constant equal to 1. So it is really a distance function, what you expect. And from that, you already conclude that V is diffeomorphic to M cross an interval, where sort of the metric is given by some suitable smooth family of a matrix. And then finally, you can do some further computations to compute the Clifford action of the covariant derivative applied to the distance function. So you get some formula for that. And once you have that formula, you can, because this action is non-degenerate, you can deduce something about the Hessian of the function x. So the Hessian of x will be given by something concrete, and it's minus 2 over n times f of x gx. And that is already enough because if you control the Hessian, in this way you already see that this family of metrics must actually be given by a walk product. And that is how you in the end conclude the rigidity statement. And I think I will stop here. And thank you for your attention.